So, okay, we're going to begin the contest now. Just to be clear, we're going to begin the contest now. You have a total of 25 minutes. You have a total of 25 minutes. I advise you to use 20 for your pitch and have 5 available for questions. I advise you to use 20 for your pitch and have 5 available for questions. Okay, if you could do 18 and have 7 for questions. Okay, if you could do 21 for 7 for questions, but you got 25 minutes. 4 for questions, but you got 25 minutes. And everybody knows the rules. 30 points for cost, 30 points for design quality, 20 points for operational design quality, 20 points for operational simplicity, 20 points for schedule. Okay, the team to follow you will be by Skype. That's Team Russia from Petersburg. Okay, the team to follow after that's the only Skype team. All the others, as I understand it, are actually present. We have a very distinguished group of judges here. Pete Worden, the former director of NASA Ames and head of technology development for the Strategic Defense Initiative before that, is one of our judges. He'll be speaking here tonight. Peter Nikoloff from Australia. He's the head of an aerospace company there. Myself, Tony Muscatello from NASA Kennedy Space Center, and Jürgen, who is from the German aerospace industry. That seems to be what we got. And without further ado, let's get started.
All right. Mic is working, right? Okay. Thank you, and hello everybody. We are Artemis, and we are here to present the conceptual design that we came up with for the Gemini Mars competition. Throughout the presentation, we will be talking about the various aspects of mission design that went into completing the design, which we'll present in today, going from the trajectory optimization and design, the interior design, all the subsystems, risk analysis, cost, and eventually we'll bring it to a conclusion. The team members are, there's 12 of us. Unfortunately, you only see 4 of us today, but it's a cooperative effort done in cooperation with the Pennsylvania State University and the Wrocław University of Technology in Poland. And the 4 of us presenting are representing both of these 2 parts. We have various mission statements, and the first mission objective is to make sure that the mission design is at top quality. And then we have the mission objective is that the trajectories should fall within the time frame that we were given, 2018 to 2024. Oops, sorry. Additionally, the astronauts must must depart Earth and come back in good health and safely. Additionally, we need to minimize the risk and maximize safety. We need to minimize the cost. And also, we must minimize the complexity for the overall mission design. So we started looking into trajectory options during the time frame that we were given, and we saw that there are a multiplicity of various options. The first one coming from short Earth-Mars, Earth flyby opportunities in the early 2018s, and then even flybys using Venus in 2021. But another very interesting and scientifically appealing trajectory was the Earth, Mars, Deimos, Earth trajectory. So our mission actually picked this trajectory because not only do we have more time for the development of various subsystems, but we also are encountering Deimos at an altitude of roughly 50 kilometers. So here you see the results of the trajectory optimization, taking into account the C3 requirements that we had for the various launches that we looked at, and also for Deimos flyby solutions in blue. And the solution that we found is the one in October of 2024. Here you see the actual flyby that we're performing. And as you can see, the spacecraft comes very close to Deimos and also relatively close to Mars. And it it does a flyby of Deimos at roughly 50 kilometers in altitude. And here in the graph in the middle, you also have the direction of the Earth and the Sun as a reference. So now I'll pass it over to Shimon, who will be talking to you about mission architecture.
Thank you, David. While designing the mission architecture, we had to take some requirements into consideration. The first one was we needed to have a launch stack that is capable of putting us in the transmar injection of the 28.7 kilometers. We needed to have on board a re-entry vehicle capable of returning the crew from suborbital speeds in safety. We also have to have a pressurized compartment that allows the crew to live, work, and exercise comfortably. And we needed to take on board the life support systems and the exercise equipment. We needed to fill this life support system with the food and water for the long duration mission. And we needed to use a hardware that is preferably flight proven or will be flight proven the 2024 time reference. While designing the mission architecture, we have a couple of launch configurations in mind. We started thinking about 2 Falcon Heavies, which require one orbit rendezvous operation, but we rendered it impossible because of the too low payload. It can do a 15 metric tons payload to transmar injection, or a 17 metric tons if refueled on orbit, but we think that it's never been done before, and it's much too risky to do it first time on this time frame. We thought about delivering full cryogenic stages with the Falcon Heavy. However, the SpaceX pod right now doesn't have the liquid hydrogen infrastructure, so it could be the launch pad could be leased from a different launch pad could be leased. However, it increases the risk of the mission substantially because someone might just refuse to lease the launch pad. We also thought about the 3 Falcon Heavies. However, this would require very complicated on-orbit assembly. So we went into the SLS Block 1B. However, it's very low complexity. However, we would have to use the Orion instead of Dragon, or have a test aboard on the SLS Block 1B. And also we'd have to develop an adapter of 8.4 meters to 3.6 meters for the Orion, for the Dragon. And actually, more cost-efficient way is to actually launch an SLS Block 1B and the Falcon Heavy. So we would take the Dragon capsule on board of the Falcon Heavy. So as I said, we had an Orion and Dragon V2 capsule in mind. These are only capsules right now that are capable of returning from a suborbital speeds. However, the Orion is almost 3 times heavier than the Dragon V2 and only 2 times more spacious. And the awkward conical shape of the capsule, we just decided to go with a bigger orbital module instead of bigger capsule. And we also have only crew of 2 on board, so we don't need huge capsule. So we thought about using different orbital modules. However, we've decided to go with the more traditional CAN design and we were left with Cygnus and MPLM modules. And because we are using 2 launch configuration, we could afford to take MPLM and retrofit it with the European service module. It provides 60 cubic meters, so it's twice as much as the enhanced Cygnus. We decided to go with the SLS Block 1B, which has a capability of delivering 100 metric tons to low Earth orbit, and the Falcon Heavy, which has a capability of delivering 53 metric tons to the low Earth orbit. And this is the orbital operations. We'll start with the SLS Block 1B launch, which will deliver the large upper stage with the MPLM and the European service module. Then we'll start with the Falcon Heavy and go rendezvous and dock. And then we'll make the first burn with the large upper stage. We'll go on a medium Earth orbit and have the second burn of the SpaceX stage that will put us in the transmar injection. And here's the animation that will help us understand how the orbital operations look like. Okay, so as I say, we start with the SLS launcher, and here we can see its payload, and then we can make a very aggressive phasing orbit because of abundance of the fuel in the second stage of the Falcon Heavy rocket. Then they after they rendezvous, they perform a docking maneuver. And once the launch stack is complete, it's operational, we put it in the right altitude and perform the burns. So let's look at the interior of the spacecraft. We have a 70 cubic meters of volume inside, and we decided to use the Dragon module as an observation post. The large windows inside could provide crew with an excellent view of the Mars and Deimos. The crew would mostly live inside the MPLM module, which was fitted with the centrifuge and all the life support equipment. The lighting in the inside of the MPLM provides the aid of where the up and down is, and also have projectors that can make the mood different by changing the temperature of the light for the crew. The most innovative part of the design is the centrifuge, which could be powered by the bikes inside. The crew would exercise on those bikes and experience a partial gravity. And it could be powered also by motors, so the crew could sleep in a partial gravity during the mission. So it helps with the long duration health issues with the space, with the mission. So right now I will give the microphone to Bartek, who will talk about the systems on board.
Thank you, Szymon. So here is the schematic view of the Eclipse loop. Due to the needs of mass cost cutting, the new system for water recovery must be used. So it is the vapor phase catalytic ammonia removal. And in this table here, you can see the mass of water, oxygen, and nitrogen that must be taken with the spacecraft. And the electric power supply system is in charge of production, delivery, and storage of electrical power energy during the mission. And in this table here, we have estimated the values of power and demand of particular subsystem. We have all of the average power demand as well as the peak power demand. And in the bottom of the table here, you can see the sum with the 10% of margin. And it's not worthwhile that the average power demand is only as high as 2 vacuum cleaners. So, due to the trajectory of the flight, the power delivery must be accomplished in 2 ways, using the solar arrays as well as the batteries. So we need to consider 3 ways of work. First one assumes the full access to sunlight as well as the average power demand of the receivers, and during that period, the batteries are being charged. Second option required no access to sunlight with the average power demand. So during that option, the power delivery is accomplished by the batteries. And the third option assumes the access to the sunlight and the peak power demand of the receivers. And during that option, the power delivery is accomplished both from the solar arrays and from the batteries. We don't consider the fourth option, which would be the no access to sunlight and peak power demand, since the crew is able to manually reduce the power demand during that period. So our consideration comes to determination which option required bigger battery capacity. And here it is. The second option required 5.3 kilowatt hours, as while the third option required 19.2 kilowatt hours, the battery capacity. So the spacecraft must be equipped with the batteries, 32 cells, with the total capacity 24 kilowatt hours and total mass 147 kilograms. And the total solar arrays area is 75 square meters. So the thermal control system is in charge of keeping the operative temperature in the spacecraft. In the table here, you can see the heat balance result with 20% margin. And in the table here, you can see the mass and power demand of particular subsystem of this thermal control system. So the reliability and the precision of the navigation are the basic requirements for the mission success, and the precision is guaranteed by combining the proper system with the devices shown in the table here. The communication during the mission will be accomplished by TDRS during all the critical maneuvers on LEO. And as well as the spacecraft will reach 30,000 kilometers above the ground, the communication will be accomplished using the deep space network. And less important data will be sent using the communication with orbiters, which will send the information later through the DSN to the Earth. And right now I would like to invite Jason to tell us about the risk analysis and the costs.
Thank you, Bartek. So Our risk analysis was determined using the NASA Risk Management Standard, and we incorporated mitigation strategies in order to reduce the likelihood of a loss of mission or loss of crew. The table here is a standard risk table which you should most likely recognize. Each of the numbers in the cells correspond to different risk scenarios where the highest risk was found to be associated with potential changes in our launch vehicles, which would require us to likely have an additional launch in order to meet our mission requirements. Onto the cost, we used two different cost models. The first was an instrument cost model. The second was a subsystem cost. As you can see, the cost of each subsystem far exceeds the cost of the instruments. On the right pie chart here, this is the instrument cost broken down into the spacecraft, systems engineering, integration and testing, management, and product assurance. On the left here, you see our subsystem costs broken down further into non-recurring costs, such as the mission design aspects, and recurring costs, such as the hardware besides the testing units. Then breaking that subsystem cost down even further, we can separate out into each of the different subsystems like ADCS, power, integration and testing, and launch supports. Now, back to Davide for the conclusions.
Thank you, Jason. So in conclusion, we would like to mention that our team was an international effort of 2 different universities and a multicultural teammates. And also the mission is being accomplished using either current technologies or technologies that are being currently developed, such as the various launchers which we looked at, such as the Falcon Heavy and the NASA SLS. Additionally, modules such as the MPLM already exist. They would have to be modified, but most of the systems are actually flight-proven already. And then we also made use of a trajectory which not only performs a flyby of Mars, but also a flyby of Deimos, which could incur into additional science and observations taken from the crew during such flyby. You got it? Okay. And now we would like to show you, that is if this video collaborates, an animation of the mission. So you already saw the docking portion. Once the 2 spacecraft dock, they are in low Earth orbit. The SLS upper stage performs the first maneuver to put the entire stack into a medium Earth orbit. Afterwards, the upper stage is discarded, and the Falcon Heavy upper stage performs a second burn, which puts the MPLM docked with V2 into a trans-Mars injection orbit. And it's, of course, discarded once it's used. So the flyby of Deimos, as I said, takes place around 50 kilometers in altitude, and the crew has plenty of time to take observations and science data of both Deimos and Mars as they're entering and leaving cis Martian space. After they return back to Earth, the Dragon V2 undocks from the habitat and performs a controlled re-entry of Earth's atmosphere. Lots of flames. And as we know, Dragon is capable of performing landing propulsively, or we could also do it using parachutes as a backup resource. So now I would like to conclude the presentation. Thank you all for your attention, and if there are any questions, we would be happy to take them. Dr. Zubrin?
My question is, I saw your C3 leaving Earth was 28. What's your C3 or entry velocity on return, and what is the duration of the flight?
Okay, so the total duration, do you want to go back to the mission overall operations? So the total mission is under 2 years, and we made use of the trajectory, as I said, makes use of the Deimos flyby. The outbound trajectory lasts for about 5 months, and the inbound trajectory back to Earth, once the flyby has been performed, is 11 months, roughly. 18 months. And, I'm sorry, what was the other question?
The entry velocity at Earth or the C3 approaching Earth, either way.
Yeah, so the arrival is, I don't remember the exact number, but it's well within the specified performance for the V2 from a reentry from a regular Mars home and transfer reentry.
So it's comparable to a minimum energy Mars return.
It is within the limits of the heat shield. Yep, I think it's less than. Yeah, I don't remember. I'm sorry, I don't remember the exact number. It's in the report, but we compared it to what SpaceX is hoping to do for the heat shield, and the reentry velocity is good enough. I mean, the flames you saw are part of the animations, but.
So this is a 2-year trajectory, therefore it's available almost.
Well, with the Deimos flyby, no, but otherwise. Yes, there are other trajectories that are available, but with the Deimos flyby, as you saw from the result graph, they're a little bit rare. But with the additional time, we also have time for developing the other subsystems for the entire spacecraft assembly.
Yeah, I just wanted to. The Deimos thing is really cool, except that there's possibility of a lot of debris from meteor impacts on Deimos. Do you have some sort of debris mitigation or?
So Deimos, as we know, doesn't have much gravity, and we're zipping by, at an altitude of 50 kilometers. But that is almost no concern as far as.
But I mean, there may be debris.
Are you talking about the dust from the surface?
Yeah, debris from Deimos itself, because as it gets hit by meteors, it stays in the vicinity in the orbit. So so the question, we don't know how much debris there is in the.
Right. System. Well, we are almost twice as far from Deimos as its size, so we don't have any concerns about the dust within, on the surface of Deimos. But as far as debris, both the Dragon and the MPLM are shielded with the micrometeorite protection.
Sorry, I've got a quick question. You've gone to the complexity of doing artificial gravity. So that's obviously going to add weight, and it's not a very big diameter spacecraft. What sort of made you go in that direction?
I'm sorry, could you repeat the last
The artificial gravity generation. Why did you make that decision? Because it's obviously going to add weight and complexity to your mission.
We thought that the duration of the mission is such that we require some sort of exercise on board, and we think that it's not sufficient to just make them run on treadmill. We wanted for them for almost half of the day to be in partial gravity or even full gravity if we decide to spin the whole centrifuge fast enough. But we will have to have sort of experiments on this to see if it doesn't create any wobble on the whole spacecraft.
I was wondering how you're planning for the SLS 1B. How does that fit with NASA's plans for having those available?
Those should be available in time frame of 2020 and 2023. So we give a 2022. So we are actually waiting extra 2 years for the first missions to be performed. So we hope the launcher will be available in a later time frame. That's why we also chose the later trajectories to have also all the other equipment ready, the ECLS, the artificial gravity centrifuge. We want to have every subsystem ready. That's why we decided to go with the late trajectory.
So would NASA need to redirect one of those SLSs to this mission, or would you have one built specifically for this mission? How do you
well, with the frequency that they're currently talking about, and that may change, but that's not really up to us. They're thinking that they could launch once every 6 months or even once a year, depending on the capacity. But this one would not interfere with any of the planned missions so far.
Okay.
My question goes direction of crew safety. What did you foresee in order to make sure that if you have equipment failures, you have redundancies allowing the crew to survive? Especially the ECLS, that is a problem area.
The subsystems? We take only one Eclipse system on board because of the mass restrictions. And again, we decided to go with the later trajectory, so the system will be tested. And of course, we can take in consideration that the life support system would fail. However, this is a loss of crew scenario because it depends when it fails. If we fail between the first and the second burn, we could do an abort to Earth option. However, if we are after the trans-Mars injection and the equipment tragically fails, that's unfortunately the orbital mechanics do not allow for the quick return of the crew.
Yeah, and the ECLS is based on which design, existing design?
I'm sorry, could you repeat, please?
The ECLS you foresee that is based on which equipment and which design?
What is the Eclipse system?
I mean, did you assume ECLS equipment from the ISS or your own design or whatsoever?
The ISS was the starting point, but we tried to, close the loop, so to speak, so have a closed loop Eclipse system. However, as Shimon said, there are some risks that are being taken. Of course, if things happen, within the first burn or so, we can recover. Otherwise, recovery is not possible for, say, during the flyby, for example. If you'd like more details in the report, the risk and mitigation sections has all the subsystems risk and with the equivalent mitigations that will be taken as shown by Jason in the risk matrix.
Yes, I would like to add in terms of the risk management, we also see that the water tank is placed on one side of the MPLM module. Also on the same side, there is a European service module which contains the hydrogen tanks, which are also pretty dense liquid. And in terms of a solar flare, we might orient the whole spacecraft in a way that the dense hydrogen tanks and then water create some sort of a shield. We could then take the crew in the put it in the Dragon module to have all the also equipment and all not that much, not dense, but every centimeter counts for them to wait out the solar flare.
Right. Thank you very much.